All right, this is walkthrough 510 section textbook on design. This is a big chapter section. It's really the summary of everything that we've done in this chapter up until now. Okay, so you're going to use moment capacity, shear capacity, deflection, all those issues or all those conditions to design a beam, which means select the beam. Okay, so again, there are two overall conditions that we must satisfy, as we should know by now, is strength and serviceability. Right, so strength and serviceability. And again, the strength side from the standpoint of the beam is M in shear. Serviceability that we've been dealing with has been deflection. Okay, once we now we have all this experience with shear moment capacities and calculating deflections, we ought to be able to, given a loading, a lateral bracing condition, and a deflection limit, select the lightest possible beam that would satisfy those items. Okay, so again, it could be controlled by strength or serviceability, so we have to check them both. Okay, so strength, certainly bending, right? Our M max has to be less than or equal to our phi M then, or less than or equal to Mn over omega. Okay, and that our nominal moment over omega, right? Okay, again, M max for LRFD would be MU max, and M max for ASD would be M applied max. Again, that comes from your moment diagram. Same with shear. VU max has to be less than or equal to phi V sub n, or VA max has to be less than or equal to Vn over omega. Then the other condition is deflection, right? So again, there's other serviceability conditions, but deflection has to be one of them that we're probably most prepared to work on. So again, we could say if I have a delta live load limit, right, of say L over 360, and let's say, I don't know what the span is, but let's just say this works out to be 0.75 inches. Then I can have my live load, delta live load max, right, based on my loading. If I calculate that loading, like whatever it is, all over EI, right, and I substitute in E for 29,000, right, for steel, I can end up with with an expression of some number over I. And again, I'm just going to say 1, 2, 3, 4, 5, whatever that number is, right, based on our calculation using equations or using moment area theorem, conjugate beam, any of those. Once I have these two pieces of information, how much am I allowed to deflect and what am I expecting to deflect? Then I can set them equal to each other. So I can put 0.75 inches equals 1, 2, 3, 4, 5 over I, and I can calculate I minimum for that condition. And I minimum, in this case, be live load, right, would be 1, 2, 3, 4, 5 divided by 0.75. So I would need a moment of inertia of 16,640 to satisfy this deflection limit. Okay, so now between the two conditions, strength and deflection, I can pick a proper beam size. Okay, it is a process, and again, this process is what I think works based on my experience. Again, it's kind of will evolve as you become more familiar with it. So you might want to, just again, you have to make notes and see what works for you. So if I first think of design criteria, primarily my analysis, okay? I want to gather some information, okay? And one thing that has a major impact on the strength of beams is the unbraced length, okay? So I want to make note of that immediately. Is it continuously braced, which means unbraced length is 0? Is it unbraced for 10 feet, 20 feet? Certainly the larger the unbraced length, the larger the beam's going to be. So I can use that as a piece of information to help me mentally prepare or guess what the beam size will be. I need to have self-weight. Maybe the problem statement includes the self-weight, which would be fine. That's probably easiest for you at this point, because if it's in there, then I don't have to worry about checking it. If we have to include self-weight, we could do one of two approaches. I could take a guess, maybe 125, or let's say 110 pounds per foot. I'm guessing at 110 pounds per foot. Again, it's a guess. And I can add that into the loading now and then verify it at the end. Okay. All right. So let's just keep that in mind, 110. Then, so then I do my analysis. So I have my shear diagram and I have my moment diagram. So now I can calculate or determine my maximum values. Again, that's what we did in statics. Okay. Now, once I have my strength conditions, now I want to do my serviceability check. Okay, how much moment of inertia do I need? So again, problem statement, right? This is what's nice about being a student. You're told what the problem is. When you get out and practice, you have to determine what the problem is. Okay, so from the problem statement, maybe it specifies a live load limit. Maybe it specifies a total load limit. Maybe it doesn't specify any deflection limit. And in that case, academically, I'd say don't worry about checking deflection. It's just a strength check. But in practice, you need to check strength and serviceability. Okay? So these limits will tell us what our maximum permitted deflection is. And again, in my example a few slides ago, I just said I'm going to assume 0.75 inches, all right, for my delta max, whatever it is and whatever it's for. So that gives me my permitted deflection. Then I apply then I calculate my deflections again using service loads only, and I want to put it in terms of load divided by I. So in my previous example, instead of being this number, I made it 1, 2, 3, 4, 5. All right. So again, whatever the limit is that we're trying to address, I want it in terms, use the service loads for that type of loading. And in the example I made before, I made it 1, 2, 3, 4, 5 over I. So then I set those two equal together, and that's where I got 0.75 equals 1, 2, 3, 4, 5 over I. And then my I minimum became that 16,460. Okay, so that's the moment of inertia. Again, remember, we always want the maximum of the two moments of inertia. Okay, we want to find the minimum moment of inertia required, I required, by taking the maximum of the whatever limits we have. Okay, because if ILL is greater than ITL, ILL is going to control. We got to have something that satisfies the moment of inertia required to limit the live load deflection, or whichever one is controlling. Okay, so now I can make a summary of my design criteria. All right, I'm going to have M max and MA max. I probably should put in there, make note of what LB is. Okay, keep that in mind because it's certainly needed. Then we have our moment of inertia. Okay, so now I can do the design part. Okay, I want to select a beam based on moment. typically the controlling things are moment or deflection. Again, sometimes deflection controls, but for sure I can say not shear. Shear hardly ever controls, so we check that last, do this last. So we're going to check moment, then deflection, and then we'll move on to shear. All right, so again, if I have an unbraced length of 0, which means it's continuously braced or relatively short, and again, what's relatively short mean? I guess I'm saying relatively short means an unbraced length less than span divided by 5. And if you have a relatively short unbraced length or an unbraced length of 0, your best friend is table 3-2, because you can select the beam based solely on my plastic moment capacity. Or, my plastic moment capacity, again, if you're using LRFD or ASD. Okay? Based on that, you can look for in the moment column, here or here, and you pick your beam. Let's say it's a 16x31. You want the one that's in the darkest, the bold one of this group. So you see here, what's my moment capacity? Here's my unbraced lengths and my moment of inertia for deflection check. And then my shear capacities, which we'll check those at the very end. Okay? But if you have a really short unbraced length, table 3-2 can find you an answer pretty dang quick. Okay? If it's greater than, if we have a larger unbraced length, then we have to go to table 310, right? And this is where you see the curves of each beam size plotted for the continuum changing in unbraced length. Okay? So now if LB is greater than 0, or it seems like that's longer than LP, the values, we can start with table 3-2, but we're most likely going to go to table 310. Okay, so again, based on table 310, let's say I have a moment capacity of, or a moment requirement of 160, and I have an unbraced length of 9 feet. I got to come out to here and find out where this combination resides on this table. And then I'm going to go up and to the right till I hit the next solid line, which looks like this 14x34. Okay, so 14x34 would be the lightest beam that would satisfy that condition and strength. Notice that the moment capacity of this beam is up here for an unbraced length of 9 feet. So this would be phi m sub n, or m sub n over p, or omega, right? So that tells us what our maximum permitted moment is, and then it tells us what beam size we have. So then we can go back, and once I have that beam size, in this case 14x34, I can go to table 3-2, and I can see that I have a moment of inertia of 340, and I can check my deflection criteria. Okay, so that will help me with an unbraced length. Okay, again, it assumes C sub B is 1. Okay, and if you find out that you're kind of at the low end of that stress ratio, that or utilization ratio, all right, if I take my max moment, my MU max or my MA max, and I divide it by phi m sub n, and I'm saying if I'm close to 1, it's probably better if it's like closer to 90%. If I'm close to, say, 0.9, let me change this to 0.9. I might want to consider using C sub B, okay, but I'm going to need a C sub B of 1.1 in order to overcome that value, right? So when this ratio is 0.9, that implies that we probably just missed the beam size, right? Again, this is a guess. I'm just taking a guess at a 10%. If my strength is 10% less than what I need, or yeah, my required moment is about 90% of my provided moment, then I'm thinking maybe I could use C sub B and get a smaller beam size. So I want to evaluate C sub B. I want to look in the region of maximum moment with a large unbraced length and a large change in moment over that unbraced length. If I have all those conditions, C sub B should be greater than 1.0. Hopefully in this case greater than 1.1. Okay, but all C sub B will do is help you. Okay, if you forget to check it and leave it C sub B of 1, you're going to be fine. The beam size will be adequate. It may be a one size or so heavier than it needs to be, but it certainly will work. So now, once I establish C sub B either through table 3.1, right? Remember that looks like this. Okay. Again, for specific loading conditions and bracing points, you can get a C sub B versus using the equation, right? You could use the equation to calculate C sub B from F1-1. Then you can go into the table with your max moment divided by C sub B and pick that from a table. And again, if that works, great. If not, you got to go revise, pick a bigger beam size based on what you get out of table 310. Then you might want to go back to table 3.2 and take a look at the LP, LR, and all these values, right? Because all these values are contained within the specification table 3-2. Okay, so now serviceability verification, right? I get the moment of inertia of the beam I selected based on moment. I have the required moment of inertia from my analysis. If my provided moment of inertia is less than my required, then it's being controlled by deflection. I have to increase the size of the beam in order to get my moment of inertia that I need. Okay? And then once I have that, once I have a moment of inertia that exceeds the required moment of inertia, again, I can use table 3.2 to look up these values. Okay? And if I'm already starting out and this is greater than I required, that's great. Just go and check shear. And shear is a pretty easy check because it's in the table 3-1, right? Again, table 3-2. If you look at table 3-2, here's your shear strengths. Okay, so you definitely want to look at table 3-2. If not, you'll have to use the calculations, which again aren't tough, but you'll have to use the calculations. Okay. Now, the last tidbit of check here is the self-weight I assumed, if I had to assume a self-weight, adequate? Is the self-weight maybe specified in the PSF also adequate? Okay. So we want to make sure that the dead load that we included in our design is adequate. Okay. If the best thing for you right now is if the problem says dead load is included, then you're off the hook. But if you had to assume some sort of dead load, you have to verify that the dead load you included was adequate, or if you need to add some more. So if the weight of the beam you selected, so say I picked the W, let me think, what we got, W, again, I'm working 21 by 141. I don't know if that's a real beam or not. W21 by 141. That's what I came up with. But I want to check that against what I assumed. Okay, and if you look way back here, if I come back to here and I said, okay, on slide 4, I just guessed and said, okay, 110. All right, so now if I have 110 in my, I have that in my design, that means I need an additional 31 pounds per foot additional. All right. So if I take my 141 minus my 110, I need to add 31 pounds per foot. If I'm doing LRFD, I just take that 31 multiplied by 1.2 to get my factored dead load. And I know for a simple span beam, right? Simple span beam, which is mostly what we're dealing with, that if I have distributed load of 31 pounds a foot, I'm going to get a WL squared over 8 moment. And I can just add that. Again, it's going to be the same for LRFD or ASD. It's just a matter of, do I multiply by 1.2? I can take this additional moment and add it to the moment I use to select the beam. Okay. And really, I can just add it to the maximum moment. I really don't care if the maximum moment occurs at a different location. It's not that great of a impact. Okay. All right. So now I add that little bit of additional load and moment to the moment I use to select the beam. And if it's adequate, then I'm good. If not, I need to pick a bigger beam and kind of recycle the process. Okay. Again, technically it adds additional deflection, but again, you got to use your judgment. All right. A lot of what we're doing is we are developing engineering judgment. Okay. And it's hard to know when enough is enough. I struggle with knowing when enough is enough. Okay. I always want to make sure everything's just perfect. Okay. Oh, man, we never talked about it being compact, right? Don't forget your compact checks, right? But the good one, the good idea, or the good saving grace is that the tables in the steel manual already account for if a shape is non-compact. Remember, the only non-compact condition we might have is a non-compact flange. Okay. So we might have flange local buckling, but the tables, if you use the tables, they already have that in the system. Okay, that's already accounted for in the design of the tables. Okay. If you're not using the tables, then you certainly need to check your compact conditions, or if you're using a built-up shape. Okay. So again, if you're using standardized shapes and the tables, non-compact flanges are already accounted for. All right. So again, I implore you to not use the tables unless you know how to at least calculate the values one time, or review them every once in a while so you're familiar with it. Design is an iterative process. Okay, you may go around the bases a couple times. Okay, the objective is typically to select the lightest beam by weight, so we want the minimum pounds per foot possible that does the job. We typically measure economy by weight, but sometimes other factors do come into play, right? Every time you put a different beam size on a drawing, it means another piece of steel that needs to be pulled from the pile for fabrication, another different type of piece of steel, a unique piece of steel on the site that the erector needs to sort through and build or erect. Again, but those cost savings are hard to justify to your client because you typically don't have a bid when you're doing the design. So you want to give it as light a structure as possible. Okay. Now, if you happen to be design build, you're both the erector and the designer, which has its pitfalls also. Your decision process might be a little different. Okay. So I think that's it. I think that's a great summary of design, if you will. It's a great summary of the entire process of beam strength and beam serviceability. So if you have questions, I would ask you to give me a call or send me an email. Okay. So thanks and good luck.